So just a little bit to go over this once more, there are oftentimes two ways to define variables, and we've talked about this a little bit before. The difference being conceptual and operational definitions. So conceptual definitions are those that define variables at some theoretical level, and these are often widely agreed upon in a specific field or research domain. Even though that's not always the case, and sometimes you will have multiple conceptual definitions. But that's much more common when a particular field is still trying to figure something out, and there are a few different yet distinct ways of approaching some type of variable when, like I said, we don't yet know exactly what it is, and that will slowly ultimately tend to converge on a single conceptual definition, which could be one or the other, or it could ultimately result in being some combination of the ones that were originally put forward. That's actually quite common as we're developing new knowledge. On the other side, we have operational definitions, or sometimes just abbreviated to operationalizations. And these are referring to the specific ways in which we measure a variable, or the way in which we quantify that variable itself. And note that we're still, in a way, thinking when we talk about conceptual definitions ultimately, but you oftentimes have difficulty measuring them at that level. And so operationalizations are the specific manners in which that is measured. As it says here, please note that there oftentimes can be many operationalizations for a single conceptual variable, and this is true at almost any point during the time that the variable has been thought about. So even once a conceptual definition is quite crystallized and solid and no longer really debated, it is still possible to have many different forms of operational definitions, and in fact, one could argue that there is some strong benefit to that as well. So there are some good examples to distinguish between conceptual variables and operationalizations of variables in your textbook, but here's just one more in case, and we'll talk about fitness. So before even getting into how we're going to measure this, it's important to talk about what type of fitness we're even referring to, because there are, technically speaking, multiple forms. Most often we think about physical fitness, but mental fitness is a thing as well, along with biological fitness. And those all refer to different types of things, and it would be kind of strange to subsume them all into fitness, even though one could, I suppose. So let's stick with physical fitness. We could define this at a conceptual level as the degree of physiological health that an individual has, along with their ability to perform physical actions for extended durations, and especially without undue pain. Now, please note that there's a lot of ambiguity or wiggle room, we could say, in this way of defining something, because how would we actually establish physiological health, and is there only really one way to do that, along with what counts as physical actions and would all physical actions count the same, and what really is an extended duration? Is it 10 minutes? Is it 10 hours? And so you can see here that the conceptual formulation of this, and please note, I don't know if this is an actual definition of physical fitness, it's just what I thought of it as and thus wrote it down. But you can see in the way that this is defined, there's a lot of ambiguity in how you could potentially go about measuring and analyzing physical fitness, but this gives us an overarching sort of theory or framework within which to work. So now, ways to operationalize this conceptual variable. We could measure how many times people go to the gym and use that as a proxy for how physically fit they were. So people who go to the gym a lot, we would assume that they're more physically fit than people who don't go to the gym very much. But there are also people who don't really go to gyms very often or at all and are quite physically fit. I mean, there are many people who take part in just sort of free body weight exercises and lots of cardio outside, and many of us would describe those individuals as quite fit. And so does that mean how many times people go to the gym is a bad measurement of fitness? Well, it might not be the best, but this is also to illustrate that one way of operationalizing a variable does not actually have to capture all forms of this type of variable. Oftentimes we will have multiple different operationalizations, which we will all use to put together to create one larger cohesive image. So just to keep going on this, we could, for example, use how much muscle mass an individual has as a way of defining fitness, such that the more muscle mass a person has, the more fit that individual. But now, what about long distance runners? Long distance runners are arguably incredibly fit because of the distances they are able to cover continuously, but most of them tend not to have a significant degree of muscle mass. In fact, many of them are very lean and, well, stringy, you could say almost. And this can just keep continuing. There are many different ways in which we could continue to measure this, and ultimately none of them is going to be perfect. It's just to show that one conceptual variable can have many different forms of operationalizations. Moving on to some of the ways in which we actually measure things, the three common types of measures that you will tend to find in most literature can fall in these categories are self-report measures, behavioral measures, and physiological measures. So self-report measures are any type of measures where you are asking a participant to report on something. How much pain are they feeling? How happy are they feeling right now? How many dogs do they own? Anywhere where you're asking someone some questions and they are responding to you. Now note, it can be direct interviews, but it can also be completely anonymous, like surveys asking about prejudicial responses towards some target group. That would also fall under self-report. Now also please note that if you have someone who's not able to respond and a caregiver or a parent is responding on their behalf, we would technically still classify those as self-report measures, even though in that case the self is not actually reporting. Following this, we have behavioral measures. So your textbook refers to these as observational measures, but I have never really come across that terminology anywhere else other than this textbook. But both really work, and they're interchangeable. So behavioral measures are a method of measuring a variable by recording any type of observable behavior or a physical trace of said behavior. Now please note, I'll talk about that in a second. So moving on to the next one is physiological measures, and these are measures in which a variable is recording some type of biological data. Now, sometimes people will run into a little bit of confusion when they're thinking about reaction times. Now, reaction times, technically speaking, qualify as a behavioral measure because they are indexing some type of behavior that we can actually observe, and we just happen to use a computer to measure it at a degree of accuracy that would be next to impossible with a stopwatch. It is not actually a physiological measure, even though you could argue that it kind of skirts the boundary between them. When we're talking about physiological measures, we're often almost referring exclusively to some internal feature or physiology of a human being. Things like neural impulses, electrical generation of those neural impulses, the amount of blood oxygenation that is changing when certain parts of the body are being used, different hormone levels, those types of things. Those would fall under physiological measures. Whereas for reaction times, that is oftentimes always classified as a behavioral measure. Now, there is actually a very consistent common bias when it comes to these types of measures. So oftentimes when learning about these, people tend to ask, and naturally so, which of these measures is the best? And a lot of people have a bias towards saying that physiological measures are the best, most valid, and most accurate, followed by behavioral ones, which are good but not as good as physiological ones. And finally, you have self-report ones that actually most people rag on tremendously, saying that they're the worst type of measure that you could come across. But now, the reality of it is that that's not actually the case. A type of measure can be evaluated on how well it was used and captures the variable it's trying to measure. And the modality in which you're measuring it, whether it's physiological, behavioral, or self-report, doesn't really matter that much when it comes to how accurate or valid they are. In fact, you oftentimes use measurement in one of these domains to make sure a measurement in another one of those domains is actually providing realistic data. This is unbelievably common for any type of physiological measures because most of them don't make sense unless they are in reference to some other known quantity. The ideal case really is that you're able to measure a specific type of variable in all three of these different forms, even though that's not always going to be possible, and actually in a lot of cases it isn't. But if you are able to measure a conceptual variable with all three or even just two of them, and you ensure that they agree, and by that I just mean that when you're high on one, you're probably high on the other, and not that you see that you're high on self-report but low on physiological and in the middle for behavioral. There, something is probably going on, and the chances are that it's not so much that one is more right than the other, but rather that they're measuring slightly different things. So like I said, the ideal case is when you're able to measure in all different forms and have all of them ultimately converge on what they're trying to tell you. Now, moving into additional ways of categorizing these types of measures, hopefully this is also review from a stats class when you talk about the different types of data. So you have categorical variables, which are oftentimes referred to as nominal variables, depending on what fields you're in and whether you're talking to research methodology people or statisticians. And these are just variables whose levels are categories. So things like species of plant or types of pets that people own or the colored plates that are available at a store, all of these types of things would fall under nominal variables because their different levels or the different possibilities of value that could be in this variable are all themselves a type of category. Now you'll often come across these, especially when you're reading papers or looking at data sets, where these type of variables have been coded with numbers. So I could have blue plates are 1, red plates are 2, yellow plates are 3. But notice that all those numbers are in this case is a key. They're a shorthand way of referencing the different categories, but they themselves don't actually hold any additional information, right? Like blue plates are not somehow ranked higher than red plates just because they have a 1 versus the red plates having a 2. A lot of this comes because of the way many statistical programs are designed. Many of them, especially more previous generation ones, had difficulty dealing with text when you were trying to incorporate it into a data set. And so oftentimes what would happen is that you would just code them and then have a decode sheet somewhere where you indicated for each variable what all the numerical values actually meant. More modern command line based statistical programs don't really suffer from this very much because they're able to operate on the sort of high level language words as easily as numerical values, but once sort of tradition sets in, we tend to keep using it. Counter or next to, let's say, these nominal variables are quantitative variables. We'll talk about 3 subsets of these in just a moment, but these are any type of variable whose values can be recorded as numbers, and those numbers have some meaning unto themselves. So how many pieces of toast I have left in the freezer, what is the temperature outside, how high is my IQ level, all of these types of things would ultimately all fall into quantitative variables. So the 3 types of ways of differentiating quantitative variables, ultimately we talk about them in terms of the scale on which they're measured, but those fall under ordinal, interval, and ratio. So ordinal are ordered variables. So these are any type of variable where the numbers represent the order in which those various items or levels fall in. So class ranking, race like a car race or running or something like that. So race ranking or I don't know, anything like that basically, where you could have an index of first, second, third makes sense when you talk about it, but there's no way to establish if the difference between first and second place is or is not the same as the difference between second and third place. For example, let's say that you had ice skating in the Olympics, so like actual like demonstration ice skating or figure skating, I think it's called. You could have a really, really close competition between the 2 top contenders. So silver and gold are just super close together. But because those 2 are so good, they blow all the competition out of the water. And so the one who wins bronze is nowhere near first and second place, even though technically they fall in third. So that would be an example of an ordinal scale or ordinal measurement. Following this, we have interval scales, and these are oftentimes confused and mixed up with ratio scales, but just sort of follow along, I suppose. So interval scales are scales in which the numbers have even distances between them. The difference between 1 and 2 is the same as the difference between 10 and 11, which is the same as the difference between 100 and 101. Interval scales, however, do not have what is known as a true zero. And what we mean by a true zero is that a zero value represents the absence of that variable. That would be a true zero. Interval scales do not have this. So an example that is used widely is temperature. So whether you're using Fahrenheit or Celsius as your preferred means of establishing temperature, in both of those cases, it is possible to have negative temperatures of different varieties, and 0 degrees in either of those measurement scales does not actually indicate the absence of any temperature or heat whatsoever. If you move on to ratio scales, they're very similar to interval scales in that the distance between each subsequent value is the same. So the difference between 1 and 2 is the same as it is for 9 and 10. But ratio scales do have a true zero. When you have 0 on such a scale, it means the absence of some variable. So counts are a good example of this. I could have 2 oranges and I could have 4 oranges, and I can have 0 oranges. But when I say that I have 0 oranges, it means I have none whatsoever. I don't have any oranges. And it isn't really possible for me to have negative oranges because 0 there is the last and lowest amount that I could have. In this case, it is none or 0. So that's really the primary difference between ratio and interval scales. Please note that there are statistical tests that apply to all 3 of these different forms, though for the most part when you're taught statistics in your college classes, you'll take maybe a couple, maybe a few more stats classes. Almost all of them will predominantly focus on interval and ratio scales, and a lot of the stats for those ultimately work the same. Now, one last note in reference to your textbook. So it talks about intelligence or IQ values as falling on an interval scale. And this is largely accepted, or at least we operate on IQs in this form to make our statistics easier. And this is largely because an IQ of 0 doesn't actually mean anything. It doesn't mean that you have no intelligence of some kind. And also, most of the current IQ measures don't actually allow for a value of 0. But that being said, we're not actually 100% sure on whether the intervals themselves are actually consistent. So for example, is the gain in intelligence, let's say, from moving from an IQ of 90 to 95, the same as it is from moving from 105 to 110, or from 135 to 140? Now, if we could somehow establish that that additional 5 points gives a consistent benefit across all 3 of those cases, we could definitely say this is an interval scale. But that's something that's really hard to actually demonstrate, and as far as I know, no one has actually demonstrated that. So please be aware that even though we'll treat many variables as interval and ratio variables, there's sometimes some assumptions that sort of sit behind that, and oftentimes we don't really talk about them as upfront because we want to jump to the results as those are more exciting to most people. But this is something to pay attention to when you're consuming literature. Further on this note of intelligence, to show just how ultimately arbitrary it is we're actually still debating about what the heck the IQ tests are actually measuring. But until you really get into like factor analysis, statistics, and going more into that kind of field of psychology, that's not really that relevant, I suppose. But the main thing to take away from this is just that sometimes we'll treat variables in this way, but they're not actually 100% this, right? So like even if you were to take scales of agreement, is the difference between I neither agree nor disagree to I slightly agree the same difference in agreement as going from I moderately agree to I strongly agree? And we operate on them with numerical values as if that was the case, but is it actually? And then of course that leads into this whole other business of how specific and nuanced should we actually be, and how much should we leave that to the wayside to just make our lives easier so we can practically advance the field. There are pros and cons on either side.